Good morning. I'm Patrick Haggerty from the University of Washington, and I'll be moderating today's session. Welcome to the Sentinel Innovation Center webinar. The US FDA Sentinel System helps address questions related to the safety and effectiveness of marketed medical products. The Sentinel Innovation Center focuses on developing innovative methods to further advance Sentinel by leveraging new data sources, building new tools, and enhancing real-world evidence capabilities through advanced analytics. We've launched the webinar series to engage experts and innovators in key areas related to the Innovation Center's master plan. And with that, I'm really pleased today to introduce our speaker, Dr. Shu Shi. Dr. Shi is an assistant professor in the Department of Biostatistics at the University of Michigan. Her research focuses on developing rigorous statistical methods that provide insights from healthcare databases such as electronic health records data. She's particularly interested in multiple themes, including developing causal inference methods tailored for EHR data, automated knowledge extraction, data harmonization across healthcare systems, and post-marketing drug safety surveillance. The title of Dr. Shu's presentation today is Harmonizing Electronic Health Records from Heterogeneous Systems via Automated Translation of Medical Concepts. Before we get started, I want to address a few housekeeping things. Your lines are muted. If you'd like to pose a question, please type it in the Zoom question and answer feature you'll find at the bottom of the panel. I'll present those questions and then Shu can answer them at the end of the session. So please feel free to type those questions in as they come to you. Finally, this session is being recorded and will be made available through the Sentinel webpage, which can be found at sentinelinitiative.org. All right, without further ado, Shu, thanks so much for joining us today and for presenting. I'll turn it over to you.
Thank you so much, Patrick, for the introduction. Hello, everyone. My name is Shu Shi. I'm an assistant professor of biostatistics at University of Michigan. I really appreciate this opportunity to talk about our recent work on harmonizing electronic health records data between heterogeneous healthcare systems via automated translation of medical codes and, in general, medical concepts. So first, I'd like to acknowledge my wonderful advisors and collaborators, as well as a few institutions that provided data and support to the work. Oops. Okay, so 2 years ago, the CMS, Centers for Medicare and Medicaid Services, renamed their EHR incentive program from meaningful use to promoting interoperability. So basically, we're at a stage that we have adopted electronic health record systems and we're constantly collecting data. The next goal is really to improve the sharing and integration of healthcare data across different healthcare systems. A key challenge to promoting interoperability is the lack of semantic interoperability. So here, semantic means the interpretation and meaning of those medical concepts and codes when they're actually used to document what happened to the patient. The reason is that we know EHR data do not talk to each other. And here's a little bit background about what we mean by EHRs do not talk to each other. When we talk about EHR data, we're talking about an ongoing stream of patients' medical record in the form of both structured and unstructured data. The structured data might include medical codes, lab tests, or drug codes, and unstructured data includes physicians' clinical notes and medical imaging. In this talk, we're going to focus on structured data, and I'm going to take the ICD and CPT codes, the medical codes, as an example to illustrate the method, although it's generally applicable to structured and unstructured data. So for example, at a visit, the patient might come in with cough and fever, which are documented by ICD codes, and then the physician may run some chest X-ray, which is documented by the CPT code. The ICD and CPT code have been called billing codes because what happens next is a bill will be generated and will be sent to the insurance company for reimbursement. So such codes have really been standardized in order to create a common language between the healthcare provider and financial departments, as well as across different healthcare systems. That was the hope, but the reality is there's not a centralized coding rule. In particular, because of financial incentives and system heterogeneity, different healthcare providers may choose to use alternative codes to talk about exactly the same thing. Here I listed 2 different ICD-9 codes, and they both talk about shortness of breath. Dyspnea literally means shortness of breath. Because 2 codes might be talking about very similar concepts, we often see that one system chooses to use one particular code exclusively and never use the other code. Now, in addition to that, the code versions are also constantly upgrading. In 2015, we switched from ICD-9 codes to ICD-10 codes. In a few years, ICD-11 is coming. So medical coding has really been inconsistent, both between healthcare systems and across time. Now, what's a consequence to that? Why do we care about this? Suppose we have 2 healthcare systems. We got the raw EHR data from system A and system B. And let's suppose we used the Sentinel common data model to align the data elements into a unified structure such that we can readily apply algorithms or statistical models to the data sets. Now, suppose we got some gold standard label from system A, which allows us to train either phenotyping algorithm or causal inference models that at some step identifies anaphylaxis. And let's say a key identified predictor from the algorithm is 786.09, this ICD-9 code that represents shortness of breath. Now, after we train the phenotyping algorithm using data from system A, we might want to apply it to system B in order to identify more patients with anaphylaxis in system B. What can be a problem here? Well, one particular problem is that 786.05, this key predictor identified by this algorithm, might not mean exactly the same thing in system B. System B might have a different interpretation about 0.05 and 0.09. In fact, it might be that system B exclusively used 0.09 to talk about presence of shortness of breath, simply because dyspnea also talks about shortness of breath. So if we directly take this phenotyping algorithm that puts a really high weight or a large coefficient on this key predictor 0.05 and apply it to system B directly, then either we're missing a lot of information on presence of shortness of breath, or we're putting wrong coefficients on this key variable. So what's the consequence to that? Well, we see a lot that if we train phenotyping algorithm using data from one site and apply it to another site, the sensitivity and specificity can be dramatically dropped. In addition, if this 0.05 has been identified as a key confounding factor, then causal inference can simply fail due to incorrect adjustment of confounding bias. So note that this is not a problem of the method. This is not a problem of the phenotyping algorithm or the causal inference methods, but rather a problem of the data, something that has to be taken care of before any statistical analysis is conducted. Now, you might wonder that there exists a lot of manually created mapping, such as the UMLS, Unified Medical Language System, that allows us to unify or standardize coding practices between healthcare systems. However, in practice, people don't follow the rule. And in addition, manual mapping can be pretty imprecise. For example, if we look at the GEM mapping, general equivalence mapping, which is a really commonly used crosswalk between 10,000 ICD-9 codes and 60,000 ICD-10 code, you can see that in addition to exact mapping, there are also one-to-one approximate mapping and one-to-many approximate mapping. Also, within each type of mapping, there can be multiple scenarios. For example, one ICD-9 can be mapped in 2 scenarios, and each scenario consists of different sets of ICD-10 codes. So if your research data span the year of 2015, and you do need to merge data that are documented both in ICD-9 and ICD-10, then they might have been potentially matched with ad hoc decisions on which scenario do we choose. Now, with those problems in mind, I'd like to introduce to you a data-driven mapping in this talk, which allows us to automatically map medical codes between 2 healthcare systems, and in order to unify the languages between the systems, such that ultimately we can transport phenotyping algorithms and statistical models from one site to another. Now, before going into details, I'd like to give you a little story about how I got into this. So this is a study that I was involved in when I was in graduate school. This is a study about patients with back pain. It's called BOLD, Back Pain Outcomes Using Longitudinal Data. This study enrolled about 5,000 patients that are 65 and older with back pain. And the primary goal is to look at cost effectiveness of early imaging. We collected EHR data from 3 major sites: Hereford, Kaiser Permanente Northern California, and Harvard Vanguard. Now, before pulling data from multiple sites, we did a very simple data quality check by looking at the proportion of medical imaging and physical therapy among the total procedures comparing 2 sites, Hereford and Kaiser. Very interestingly, we saw that there's no physical therapy at Hereford, which is weird because we're talking about patients with back pain, and PT is one of the most common procedures for back pain patients. That triggered our concern about data quality issue. So at that time, I was very motivated to develop some method that can scan for variation across the full spectrum of ICD or CPT codes in order to identify more of such data quality issue. And here's what we did. A key feature of medical codes is that they are naturally collapsible into group of codes, either talking about similar diseases or talking about similar medical procedures. Here, for example, FEWAS and CCS are a very powerful tool that allows us to group codes into clinically meaningful groups. Under this hierarchical structure of codes are nested within groups, we developed both testing and estimation procedures that has been built into software that allows us to detect and quantify coding differences between healthcare systems, even before any analysis is conducted. And that's essentially how we found out that there's no physical therapy at Hereford. To close up this story, in the end, what we did is we made a phone call to Hereford and asked them, how come there's no physical therapy? And they were like, of course we have physical therapy. We just use our own code to document physical therapy. So here, HF0PT, where HF stands for Hereford, PT stands for physical therapy. This is a site-specific code used at Hereford to document physical therapy in general, and it does not belong to any of the standard CPT code. Now imagine if you were to conduct some research and you want to identify a cohort of patients who underwent physical therapy. Of course, you are going to use the standard CPT code. Now, without any pre-scanning of coding differences, this is the amount of data that you might be missing. Since then, the question that has been haunting me is, do we always have to make a phone call every time we find out a data quality issue? Or alternatively, can data tell me that HF0PT, this site-specific code that we have no idea about what it means, actually means physical therapy? Well, here is one idea. Suppose this arrow here is the medical record for one patient over time, and let's say it has been chopped into multiple timeline bins, such that each timeline bin almost talk about one visit. Now, if you look within this one visit, you will see that HF0PT is always surrounded by neighborhood codes that talk about pain, either pain-related diseases or pain-related treatments. And we know that physical therapy often appear in such a pain-related context. So we could almost guess from the context that HF0PT means physical therapy. Now, based on this idea that semantic information comes from its neighbor, what we did is for every single pair of codes, we count how many times do this pair of codes co-occur across all patient timeline bins among all patients within a single healthcare system, which will give us a co-occurrence matrix. For example, if we have 10,000 ICD-9 codes, then this will be a 10,000 by 10,000 matrix where each element, each entry tells us how many times does a pair of ICD-9 codes co-occur, how many times do they show up among all patient visits within this healthcare system. This co-occurrence matrix tells us the relationship between a pair of codes. From that, we can actually learn the meaning of each single code. And the key trick is to do a simple matrix decomposition, which gives us the top key features that describes the meaning of the code. And here's a little bit more detail about that. It turns out that the computer learns the meaning of a word exactly from its neighbor, from its context. The type of product that has been used in natural language processing is called word embeddings. So basically, word embeddings represent a word as a vector, which is a point in some language space. The two words with similar meanings will be closer to each other in this language space. It's actually the fact that the word embeddings has been around for a very long time, but it's only recently popularized due to a set of very powerful algorithm called word-to-vec. So essentially, word-to-vec trains a very simple one-layer neural network, but use it on a large amount of text data, and it turns out to perform really well. And because of the really shallow structure of neural network, you can mathematically show that one key algorithm in word-to-vec is essentially doing matrix decomposition of a mutual information matrix derived from the co-occurrence counts. Now, if you think about each healthcare system has its own language. In this language, the medical codes are like words in human language. So we could readily apply the word-to-vec algorithm to train code vectors. The reason I really like code vectors is because they're data-driven, and data tells us what's the interpretation, what's the meaning of the codes when they're actually used in practice, which can be very different from the standard coding rule. People don't follow the rules, right? In particular, if you look at this example on the bottom left, these are a bunch of two-dimensional IC9 embeddings. Usually, we know that by standard coding rule, ICD-9 codes with similar meanings should be closer in numeric value. However, here, 250 has been put together with 719.29. And if you look at the description, they both talk about abnormal glucose level, which can be related to diabetes. So those data-driven code vectors are actually picking up patterns that does not follow the standard coding rule, but is representing what's the interpretation in practice. And that's exactly what we want. We want to understand whether two healthcare systems have their own interpretation of the meaning of the codes, which has led to different coding practices. Now, that's a pretty good analogy. And the next question is, can we do language translation between two healthcare systems? Or more specifically, can we infer a mapping between two sets of code vectors that are learned from two healthcare systems, respectively? And how do we do that? Well, it turns out that the existing language translation method using the traditional word-to-vec definitely needs some tailoring. So what happens in the traditional method is that, suppose I want to do language translation from English to Spanish. Then in the first step, I'm going to generate a bunch of English word vectors, and separately, I'm going to generate a bunch of Italian word vectors. So those are trained based on either English text and then separately trained on Spanish text. Then I'm going to align the two language spaces such that I can actually talk about distance in the same language space. And then lastly, we're going to look at, for each English word, what's the closest Spanish word in this same space, which will allow us to infer a mapping between English words and Spanish words. That looks pretty good, but if you look through this whole process, you'll see that in each step, we're optimizing a different objective function, which can lead to suboptimal result. One way to solve this problem is to normalize the length of those vectors such that they all lie on the surface of a sphere. What does it mean? So if it's a two-dimensional embedding, which means each vector is a two-dimensional vector, then after length normalization, they all have unit length and they will lie on a circle. Whereas if it's a three-dimensional vector, then they will lie on the surface of a ball. Now we're going to cast this problem into a statistical framework. But before going into details, the kind of example I'd like you to have in mind is this figure in the bottom, where we trained a bunch of IC9 code embeddings using data from one particular healthcare system called Partners Healthcare. And then for the same set of IC9 code, we trained their code embeddings using data from the VA. The name of those IC9 codes are exactly the same, but the meaning of them when they're actually used in practice can be very different. And our goal is to find out whether code A in Partners and code B in VA might have different name, but the same interpretation. And we call it code mapping or code translation. Okay, so how do statisticians think about language translation? Suppose I have two matrices, I call them X and Y. Each contains n code embeddings, code vectors, and each code vector is of dimension p. What does it mean? If you look at this toy example in the bottom, I have from partner, I trained 5 ICD-9 code embeddings. Each embedding is 2-dimensional. And similarly, I trained for the same 5 ICD-9 codes, I trained their embeddings using data from VA. So these are my Y and X, and they each are 2-dimensional embeddings. In practice, the dimension of code embeddings actually ranges from 100 to 1 or 2,000, but this is just a toy example. Now, with those multivariate variables, classical regression would simply run a model where Y is equal to XW plus U. Here, W is some coefficient and U is random error. One implicit assumption that we have been taking for granted is that each pair of the response and predictor, Yi and Xi, are correctly linked and correspond to the same object. This might not be true in our code mapping setting because code one in partners and code one in VA, they do have the same name, but they might correspond to different things because they're interpreted in different ways. Now, in order to make this assumption more explicit, we're going to introduce a mapping matrix called pi. So if pi is an identity matrix, which means it has all ones on the diagonal and 0 in the off diagonal, then this model will reduce back to the classical regression where we implicitly assume that each yi corresponds to the same xi in the same row. Whereas if pi is a permutation matrix, then it's like the rows in X are shuffled such that yi no longer correspond to xi. And we call it shuffled regression. In my mind, I think of this mapping matrix as a dictionary. So if I want to translate from English word to Spanish word, then pi is the dictionary that tells me the relationship between those two set of languages. In particular, each row in pi is like a pointer. It's like one term in the dictionary that tells me for each yi, what's the corresponding xi. For example, if I look at the first yi, then I'm going to go to my first term in the dictionary, the first row in pi. In this row, the second location is 1, and the rest of them are all 0, which means the first y should be linked to the second x because the second location is 1. Now, similarly, if I look at the second y, then I see that the first location is 1 and the rest of them are all 0, which means the second y should be linked to the first x. Now, if you look at the third, fourth, and fifth, they're not mismatched, they're not shuffled, simply because the corresponding rows in pi are exactly the same as the identity matrix. The ones are on the diagonal. Now, in addition to that, recall that sometimes we might want to map from 10,000 ICD-9 codes to 60,000 ICD-10 codes. So of course, in addition to one-to-one mapping, we might also have one-to-many mapping. And that is going to be represented by a weight vector. So for example, here, the fifth y can be mapped to the linear combination of 3 codes in X. Some codes might be more important in the interpretation, indicated by higher weights. Other codes may be less important, indicated by lower weights. So this pi matrix allows us to document both one-to-one and one-to-many mapping through permutation or a weight vector. Now, if you focus on this pi matrix, it's an n by n matrix where n stands for number of codes. What does it mean? It means if I have 10,000 ICD-9 codes, then this is a 10,000 by 10,000 matrix. And that's quite a lot of parameters that we need to estimate. Now, a key prior knowledge that we mentioned a little bit before is that codes are naturally collapsible into group of codes talking about similar diseases or similar procedures. So that's quite helpful because if you think about, let's say, the first 2 rows in pi correspond to 2 codes that talk about diabetes, and the last 3 rows talk about heart disease, then it's very unlikely for code A in diabetes to have the same interpretation as code B in heart disease. So that means codes only mismatch within group. They never cross-match across groups, simply because different groups are talking about quite different concepts. The synonyms are appearing only within group. Based on this prior knowledge, we additionally assume that this pi matrix, my dictionary, is block diagonal. It's also called blocking in record linkage. So that actually largely reduced the number of parameters we need to estimate, because everything on the out diagonal that are not within the group, that are outside of the blocks, they are set to 0. We don't need to estimate those. We just need to focus on each of the block that give us the mismatch pattern. Lastly, recall that the role of this coefficient W is to align two language spaces such that we put all the vectors in the same language space to search for neighbors. When we align them, we don't want it to stretch the vector outside or inside of the sphere. We want it to stay on the surface of the sphere, which means this coefficient matrix W needs to be a rotation matrix that only rotates the code vectors, and it doesn't stretch the code vector. So another assumption we make is W is an orthogonal matrix, which essentially only rotates the two language spaces. Now, to summarize this statistical framework, in this framework, we want to estimate two things. One is my dictionary, the mapping matrix pi, and the other is the rotation matrix W. And we're going to use spherical data, which are word vector or code vectors that lie on the surface of a hypersphere. And those spherical data are actually dirty in the sense that they're mismatched. The response and predictor do not correspond to each other. So that's a pretty challenging problem. So here's the fun part. This is our proposed algorithm, and we call it I-sphere map, iterative spherical regression mapping. There are 3 key steps. In the first step, we're going to ignore the fact that the spherical data are mismatched to each other, yi and xi do not correspond to each other, and we just simply run a simple regression to estimate the coefficient W, which allows us to align the two language spaces. And then once we are able to estimate W, we can rotate the vectors and align the two language spaces. Then in the second step, we're going to look at within the same space, what is the underlying mismatch pattern by linking codes between two systems, linking codes in Y to codes in X by looking at who's the closest neighbor in the same space. And then eventually, once we have the underlying mismatch pattern, we will be able to clean the data in the sense that we can select the data, the rows in my X and Y that are not mismatched, that are correctly linked to each other. And then I can use this clean data to refine my estimation of the regression coefficient W, which allows me to better align the language spaces. So if you look through this whole process, it can actually be iterated, right? I align my language space, I match the codes between X and Y, and then I better align the language space, and then better estimate the mismatch pattern. And that's why we call it iterative spherical regression mapping. But our theoretical findings show that actually 3 steps already give us a pretty good result. In more detail, in the first step, what we do is to find the optimal rotation W via something called spherical regression. The spherical regression is nothing different from linear regression, except that the data lie on the sphere. So basically, we're trying to reduce the distance between vectors in Y and vectors in X using a rotation matrix. And it turns out that this problem has a closed form solution. So this whole optimization procedure only takes a blink. So it's pretty fast. Now, in the second step, what we do is to estimate the mismatch pattern by estimating pi. And essentially, that means we're going to match a code in Y to its nearest neighbor in X. This takes 2 steps. In the first step, recall that pi is a block diagonal matrix where each block corresponds to a group of codes. We're going to block by block run a regression model, which essentially tells us for every pair of Y and X, what's their distance. Then in the second step, we're going to look for the closest distance, the smallest distance between Yi and Xj. And in addition, we're going to use a hard thresholding procedure that allows us to distinguish between one-to-one mapping and one-to-many mapping. Lastly, we're going to use the cleaned data to rerun this spherical regression, which also takes just a blink, to refine this rotation matrix W. And then we can iterative use this procedure. Now, as statisticians, we also think about what are the theoretical guarantees of this procedure. Can this proposed method actually work? Now, if you think about the first step, a natural question to ask is, we often see that when data are linked between different sources, there are linkage error, there are mismatch in yi and xi. But can we still consistently or precisely estimate the regression coefficient despite the fact that my data is dirty? So a key question to ask here is this alignment procedure guaranteed to be insensitive to the amount of mismatch in my data? Our theoretical findings show that this estimated first step, W hat, this estimator, converges to the true value at a rate that consists of two terms. The first term talks about the inherent noise in the spherical data, which is kind of inevitable. But the second term tells us how does mismatch in the data in fact impacts the regression estimation. And we show that one necessary condition is something called sparse mismatch, which means the amount of mismatch in the data is relatively smaller, much smaller compared to the sample size, which is true for our code mapping scenario. In our code mapping scenario, we're looking at two healthcare systems, and majority of them have the same interpretation, but some of the codes might have different interpretation when they're used in system A versus system B. So the amount of mismatch is much smaller than the total amount of codes. So our alignment procedure will be guaranteed to be performing good in terms of estimating or aligning the language spaces. Now, a second question to ask is, can we correctly generate or identify the underlying code mapping? Our theoretical findings show that under certain regularity conditions, if the underlying relationship is one-to-one mapping, then we can correctly map yi to xj, whereas if the underlying relationship is one-to-many mapping, then we can consistently estimate that weight vector, which tells us which codes in X are more important in interpretation and which codes are less important. Lastly, we show that this refinement step of rerunning the spherical regression in the first step that we introduced in the first step, but using the cleaned data, will perform as good as if there is mismatch in the data, as shown in the error rate, where it only depends on the noise in the data and no longer depends on the amount of mismatch, which is great. So to further illustrate this, we compared our proposed I-square map procedure to an old language translation method for word-to-vec algorithm developed by the team led by Miklov in 2013. We call it the Google method because the authors were at Google when they developed this method. So on the left, we're looking at the arrow from the first step, spherical regression, and the last step, refinement of spherical regression. On the right, we're looking at the pi matrix, the error in the mapping. So on the left, the y-axis is mean square error for the regression coefficient, and the x-axis is increasing number of codes. As you can see, black is Google, red is I-square map. The lower, the better. So both our I-square map actually dominates in terms of the regression coefficient estimate compared to Google. Now, if you look at this dictionary that we generated, and look at the proportion of error in terms of one-to-one matching, comparing black Google and red I-square map, you can see that the I-square map actually have a mapping error that's almost close to zero. So that's pretty good performance. Now, how does this method perform in real-world data? Here is an example that looks at the translation of ICD-9 codes between Partners Healthcare and the Veterans Health Administration, VA. On the left are the trained ICD-9 code embeddings from Partners. On the right are the trained ICD-9 code embeddings from VA. So they're each color-coded according to which group they belong to. And as you can see, some of the groups, for example, the blue and purple, are actually on top of each other, which means if we don't have this grouping information, then it is very likely that we make a mistake simply because those groups are too close to each other. So this grouping information is actually quite helpful. In addition, as you can see, the whole pattern of those dots on the left and the right are not very similar. In fact, they might be able to better align with the rotation. And that is the role of the first step of space alignment between Y and X. So now, in summary, the code translation essentially is equal to space alignment and then mapping, borrowing the knowledge from code grouping. Now, in the bottom is some selected results. We're looking at, on the left, the ICD-9 code from Partners Healthcare, and mapping to, on the right, the same set of ICD-9 codes from VA. As you can see, 786.09, the ICD-9 code that talks about dyspnea, has been mapped to 0.05, which talks about shortness of breath. In fact, they are actually very similar. So it might be reflecting that in practice, at VA, people exclusively use 0.05 to document presence of shortness of breath. And at Partners, people might tend to use 0.09. In addition to that, you can also see that one code can be mapped to many codes. One code in Partners can be mapped to many codes in VA. And some lines are thicker, other lines might be thinner, which are indicating the different weights that tells us what's the importance of each code on the right in terms of interpreting the meaning of the code on the left. Okay, so now imagine if you have trained a phenotyping algorithm using data from Partners, and the key predictor is 0.09. Then when you transport it to data from VA, instead of looking at presence of 0.09, this mapping is telling us that you might want to look at presence of 0.05. So this is how we can use this mapping to guide us in transporting algorithms and models from one healthcare system to another system. Here is another example where we try to generate a mapping between ICD-9 codes on the left and ICD-10 codes on the right. So this is a group of codes within the group called suicide and self-inflicted injuries, SSI. And as you can see on the left, the top one are manual mapping from GEM, and the bottom one are data-driven mapping from our iSteerMap algorithm. You can see that on the left, each of the ICD-9 code has been mapped to the combination of 2 ICD-10 or 3 ICD-10 codes. The code that's always mapped to is this ICD-10 code in the bottom, which talks about intentional self-harm by jumping from a high place, initial encounter. And it's further combined with another ICD-10 that talks about the location of jumping. In particular, if you focus on the second ICD-9 code, it talks about suicide and self-inflicted injuries by jumping from natural sites. And it has been mapped in GEM mapping to 2 areas. One is recreation area, the other is wilderness area. However, our data-driven mapping actually only picked up one of the areas, which might be indicating that in practice, when coder tries to document what happened to the patient, they see that those 2 areas are pretty similar. So they just tend to pick one of them in order to generate the record for the patient. But other than that, the data-driven mapping actually look quite similar to the manual mapping, which is also a validation that our iSteerMap algorithm actually worked on real-world data. To summarize, mismatch corruption and linkage error are actually quite common in modern datasets, which are frequently integrated from heterogeneous sources. In terms of EHR data, it is really important to semantically match or translate the medical concepts and medical codes before the data is being fed into a phenotyping algorithm or statistical model. However, the currently existing manually created mapping, such as the GEM mapping, can be time-consuming, imprecise, and error-prone. So it's really important to develop methods that are scalable and automated such that we can streamline the whole process of data harmonization. And our developed data-driven mapping is one such mapping. And the reason I like this data-driven mapping is twofold. First of all, it does not require individual level data. If you still recall how we generate the code vectors, they are solely based on co-occurrence counts across all patients within this healthcare system. So imagine if we want to harmonize the codes between 2 healthcare systems, all we need is one co-occurrence matrix from one side and another co-occurrence matrix from the other side. And then we can use the mapping method to generate the mapping between either medical codes or other type of medical concepts. The second reason I like it is because it's unsupervised. compared to the existing language translation method, it does not rely on training labels. So it doesn't rely on existing set of dictionary for us to anchor this mapping. The whole process can be done in an automated way. So that has a lot of potential. And this concludes my talk. Thank you very much for your attention. Happy to take any questions.
Yeah, terrific. Shu, thank you for this really powerful presentation. It's clearly important to be able to detect heterogeneity and then correct that heterogeneity if you can. I want to just invite people to recognize you can ask questions. It's in the question and answer portion in the webinar feature, so it's at the bottom of your screen. As a reminder, your lines are muted and we can't unmute them, but I can be the facilitator and present your questions to Shu. I look forward to your questions, but I'm going to start with a couple as well, Shu. I think it's really interesting to look at the heterogeneity at the system level, and of course that makes a lot of sense. Have you thought about whether or not it's important or feasible to look at it within substructure, within systems, maybe different clinics or different providers? What are your thoughts on sort of looking at different levels?
That's a good question. So when we talk about like the hierarchical structure within codes, we're looking at almost like one type of hierarchical structure. There is another hierarchical structure, which is within each system, there are clinics and healthcare providers, and they might have different coding practices as well. So one way potentially to extend this method is to look at to kind of incorporate the variation between groups defined by different healthcare providers. So that's a really good point.
Yeah, cool.
Yeah.
Excellent. So what would be the next steps for somebody who really wanted to make this actionable or concrete within their research program or within Sentinel Initiative? What would they need to do?
So I think it would be good to, what I talk about are twofold. One is detecting coding differences, and the other is correcting coding differences. And I think both procedures are important. So in order to align that within the Sentinel system, we can potentially think about how to create a full pipeline of detecting differences and correcting differences, and generate actionable software programs that allow us to use them on some examples. For example, developing anaphylaxis phenotyping algorithm and see how it performs. For example, if we were able to detect differences and generate mapping to correct the differences, then does it improve the sensitivity and specificity when we apply it, when we train the anaphylaxis phenotyping algorithm from one side and then apply it to another site? So that would be a good validation as well. In addition, expert knowledge is very important, both in terms of building the method and also validating the method. For example, when we look at matching between Partners Healthcare and VA, we asked clinical experts, does those mapping actually make sense to you? And we learn a lot of knowledge from that. So I would say another aspect is to incorporate expert knowledge.
Great. So another question is it seems like it would be sensible to choose one site as an anchor site or a reference site, kind of like time zones. There's the time zero Greenwich Mean Time Zone. What would be the characteristics of an anchor site that you would like to see that would help you pick it to be an anchor site?
That's a great question. Let me first give you an example. We see that some, so the VA has more detailed coverage of all utilization of codes, whereas Partners might not show up certain rare diseases. Whereas, so in VA, we can see a lot of rare diseases. So one key feature is that it better be a large healthcare system such that it covers as much medical code endorsement as possible. So that can serve as one feature for the anchor site. And in addition, it better be a system that is documented in a really clean way such that we can generate high quality code embeddings to map to other code embeddings.
And thank you. One specific question is the computing time. If I had a pretty big corpus of data from a couple sites, how long does it take to do this entire pipeline? Is this something I could even envision refreshing in some frequency of time?
Right. So when I try to analyze the data using, I believe that was 18 million patient records from the VA, after generating the co-occurrence matrices, the whole procedure took at most hours, like 1 or 2 hours. So it's not a big challenge computationally, but I could imagine if you were to do it on a large amount of data partners, then it would potentially take much more time.
Another question is can you relax maybe to look across blocks? Because you may find things like those Henry Ford codes may not have been put in the same block, or is that really just a difficult issue to invite because you really reduce the sparseness that seems like it's so smart and efficient?
Yeah, you can potentially relax the blocking assumption. So in record linkage, in addition to blocking assumption, you can do other ways of mapping one set of records to another. And we're currently thinking about borrowing some of the idea from that and essentially from graphical models. So you're looking at nodes that represents codes from one side and nodes that represent code from another side. And we're essentially learning the underlying graphical model that links them. So that does not rely on any blocking information. And we're trying to see what's the theoretical guarantee for those type of methods. Great. I believe Jen also have raised hand.
Yeah. Hey, Chi, Shu, can you hear me?
Oh, hi, David. Yes.
Hi, yeah, great presentation, thank you. It's wonderful you make this really fairly complex stuff so accessible. I appreciate that. I had a question about the time frame used for defining co-occurrence, or maybe it's the sequence, you know, an encounter happens now, and then another encounter happens next, and then there's an encounter after that. Does it matter much how you define what means the two codes co-occur, either in amount of absolute time or just relative sequence?
Yeah, that's a very great question. So to say that back to you, when we define a patient timeline being, it's almost like we're trying to define what is a sentence in the record and what's a paragraph, if you think about EHR data as text. And it's important to define the window because that kind of controls how many neighbors are included when we count for the co-occurrence. And we have tried to look at 7 days as a window for patient visits or 30 days. So if you narrow down the window, you might really looking at one particular visit. Whereas if you expand the window, you might be looking at some certain chronic diseases, or you might be able to incorporate more information. And it really varies. The choice of the window size when we count for the co-occurrence really depends system by system. It really varies by system. We see that for system with not really high data recording quality, so documentation quality is not so nice, then we tend to use a larger window. So in order to incorporate more neighborhood information. Whereas if the data is pretty nice, well documented, then we might use a smaller window.
Thank you, that makes sense.
Good. All right, last call for questions. It was really terrific. I really want to thank you, Shu, for sharing this exciting work with us. I look forward to seeing it develop and seeing it applied and tried out. As a reminder, this session's been recorded and will be made available through the Sentinel webpage. You can find details and registration for future Innovation Center webinars on the website, sentinelinitiative.org, and we encourage you to do that and register for upcoming presentations. This concludes the presentation today. We hope we see you next time. Many thanks to you, Shu, for your excellent presentation.
Thank you, Patrick, and thank you for the opportunity. Thank you, everyone, for your time.